Thank you everyone for joining this, our latest session of our global webinar series. And my name is Wilmer Companioni, and I'll be your host and presenter for this webinar. So we like to do these quarterly launch retrospectives in order to give everybody an idea of the latest products that we've launched, or some of the key recent products that we've launched aimed at helping you solve your problems. So today we'll take a look at some of those. So our teams have all been working very hard trying to launch product to help you be successful with your designs and your challenges. So over the next 15 to 20 minutes, we'll take a quick look at some of the key products we have launched during the last quarter to help you solve and tackle those engineering challenges. And as I said, I am your presenter. And last quarter, we looked at a variety of different product launches aimed at solving different problems. And this quarter, these key product launches are all aimed at standing up to some of the challenges in the power conversion space that are seen in the industry. These devices are generally suitable for use in conditions of elevated temperatures where you can't sacrifice performance. And of course, it isn't just capacitors. Now, we will be taking a look at some of those, but we're also going to be turning our attention to some magnetics solutions that help you solve those challenges. We'll start by looking at some of our expansions into the film DC link lineup. Then we'll explore some advances in the metal composite power inductor lineup. And from that, we'll go into taking a look at some of the new offerings in the aluminum electrolytic space for automotive. And we'll close out by looking at some wireless power transfer ferrite tiles. So, as I said, I am your presenter. My name is Wilmer Companioni. I have 15 years in total of industry experience spread over engineering, design, and marketing. But despite what I would like to think, you're not here for me, you're here for the content. So let's get to it. All right. First off are the additions to the DC link, the film DC link family that addresses the extended life needs of future applications. So very quickly about DC link, sometimes multi-stage power conversion requires an intermediate DC step between the rectifier and the power inverter. A DC link cap is placed in between those two stages to allow for efficient and clean energy transfer. Caps in this area sometimes experience very high slew rates and a great deal of power transfer to it. So it's for that reason that the cap has to be capable of self-healing and able to withstand elevated internal temperatures caused by that ripple current that it sees. The addition to the DC link, the film DC link lineup addresses these challenges. Power conversion systems that use a DC link are highly prevalent, particularly throughout the power conversion space, but in particular in the industrial space, and are becoming more and more adopted in automotive applications. So finding a suitable DC link capacitor is mostly a game of managing current density with temperature performance. Some of that management means having to apply a correct derating factor so that the capacitor will last the service life of the device in which it's installed. The recently launched C4AK family of film DC link capacitor exhibits the least amount of derating necessary when compared to some of its other counterparts. Then we also have the M variant of the C4AQ, in this case the C4AQM, that has increased current density capability because of the smaller size. The M designator means miniaturized. So in this world, it's really all about pushing out performance. Technically, the C4AK is rated at 130 degrees C, but that's not the expectation, right? That is the rated temperature. But the true idea behind that temperature extension, if you will, is to provide extended service life under comparable operating conditions. So say, for example, in a previous capacitor generation, you would have had 20,000 hours of life. With this now C4AK series that's capable of higher rated temperatures, that 20,000 hour life would be actually much more so than that under similar conditions. So selecting the right DC link, film DC link cap can sometimes be daunting, right? We've got a whole alphabet soup of series available to you. So we've created this flowchart to help you along the selection process. In particular, some of the key parameters to take into account when selecting a film DC link cap is the expected life performance, the temperature humidity bias performance, and the maximum temperature that the component will see. So for example, if I need a capacitor that is capable of withstanding temperature humidity bias performance of 85 degrees C, 85% relative humidity for 1,000 hours at rated voltage, that's a typical temperature humidity bias test in an automotive application, and that particular capacitor will not see more than 125 degrees C, then the choices available to me are, for example, the C4AU when I follow this flowchart, or the R75H. So now between those two, the R75H is the longer life option. But of course, that extra life comes at a bit of a premium. So there's an economic question here too. Are you willing to pay for that extra life? So using this flowchart and using this methodology, you've somewhat helped narrow down how to arrive at the proper decision, at the proper selection point. So the high temperature story here doesn't just end with capacitors. We've introduced a recent extension or a recent addition to our metal composite inductor lineup, this Metcom series, that are also capable of high temperature performance. So first, some basics on metal composite inductors. It's really just a mixture of metal powder and insulation material and the binder that are carefully mixed together and molded under high pressure around the coil of wire, essentially the inductor itself, around the coil of wire that has been welded to that lead frame. So what's important to note here is that this is not a sintering process. The metal powder particles are not sintered together, they don't grow together. And the particles actually have to be kept from making contact with one another. This is because the magnetic flux going through the core can cause or does cause eddy currents in that core that counteract the primary flux and actually results in more losses. A good way to think of this is the same reason why many transformer cores are laminated to minimize those losses. So the same principle applies here in the metal composite inductors, our Metcom series. So the temperature challenge is that the elevated temperatures can cause that insulation and binder to break down and even create a conductive or a continuous path when the particles come into contact with one another. And that essentially ruins the inductor. The overall effectiveness of the insulation is what we call the insulation resistance. And in a 180-degree test, the newly introduced MPEV series of inductors retain a very high level of insulation resistance when exposed to those temperatures when compared to some of the competition that their insulating material might break down. And as I said, when this insulating material breaks down, you have a lossier inductor that can lead to excessive self-heating and even device failures. So using our casing tool, we can look at this in the example of a typical buck application. And the MPEV series outperforms even the conventional MPX series that exhibits less self-heating. So those elevated temperatures are not just theoretical. The automotive space has to be particularly robust against thermal overload scenarios, especially when part of a mission critical or safety system. The new power architectures, such as those based on 48 volts, can see currents up to 30 amps. And with those currents, those really, really high temperatures are possible. Temperatures that might break down your insulating material, your binder. And speaking of automotive, the aluminum electrolytics team has been hard at work bringing new packaging technologies to our lineup. This includes the rectangular pack. So the AAR70 series of aluminum electrolytic capacitors are an ACQ200 qualified flat pack device. The wound capacitor element is flattened and placed inside a low profile aluminum case. And while it seems internally like a typical aluminum electrolytic capacitor here, the magic is all in the packaging. That aluminum case, that flat aluminum case packaging has a number of added benefits. One such benefit is that the case can be easily affixed to a large metal body that acts as a heatsink. And getting the heat out of capacitors, components in general, and aluminum electrolytic capacitors specifically can lead to improved performance. The improved thermal management leads to stable ESR, capacitance. Even when ripple current is applied, yeah, that ESR does shift a little bit, but not quite as much as in a situation where there was no heat sinking. So being able to get a nice heat sink, getting the heat out of the capacitor really does wonders for it. It extends life and things like that. So it's that flat rectangular nature of the AAR70 series that makes it much more suitable to heat sink integration and affixing than some of the cylindrical counterparts. And finally, we'll take a look at some wireless power transfer tiles. I think, as we all know, wireless charging is not just for cell phones anymore. There are many methods being explored to charge the electric vehicles of the future. And really the most futuristic one is wireless charging implementation. But when you're transferring many kilowatts of energy, of power, being efficient is much more important than when you're charging a phone. It's for this reason that we continue to advance the science of our wireless power transfer ferrite tiles. All right. So really quickly, in basic electronics, we learn that flux radiates out from a wire in all directions according to that right-hand rule. When you're trying to exchange power from a transmit coil to a receive coil, the flux that is lost behind the transmit coil is flux that doesn't make it to the receiver coil and therefore accounts to lost power. The ferrite tiles can help refocus and redirect some of that flux so that more of it makes it up to the receiver coil and really improves overall system efficiency. And it's that efficiency, those efficiency gains, that are necessary to make wireless power transfer systems viable, not only technically viable, but also economically viable. Okay, so in general, all the tiles are made from our BH1T ferrite material. It's just one of the designators or one of the generations of our ferrite material. So selecting the right coil is really a challenge of matching the mechanical needs, the mechanics of the tile, with the level of power transfer needed. So if I'm seeking to have a peak power transfer level of 30 kilowatts, then according to this chart and this selection guide, I necessarily need a 16 or 20 millimeter thick tile. Any thinner, and I risk saturating, overheating, and ultimately damaging the tile, and possibly by extension, any of the attached systems. So really that brings me to the end of the webinar, where we took a quick look at some of the products we launched in the last quarter. And if you have any questions now, please submit them through the Q&A portion of the Zoom session. Or if you have any questions that come out after the fact, you can follow that link there. And please don't forget to take that post-webinar survey so that we may improve this overall webinar experience. As far as upcoming webinars, we're normally on a 2-week cadence. We're going to skip the webinar on July 5th, obviously due to holiday. And then next up is on July 19th, where some of the experts in our film group will take us through advances in film capacitor technology. So the registration page for that one will be up very soon on Engineering Center. So thank you very much. And with that, I will open it up to any questions that might have come up. All right, well, if there are no questions, this presentation will be posted and you'll be able to review it at your leisure at that time. So with that, I'll close it out, let everybody get back along with their workday. And thank you very much for attending this webinar, and we'll see you at the next one.